Hello everyone, this is another video, Matt 2015 question 4 this time. I'm just trying to get them done. I think you've got the exam on Wednesday, haven't you? So if I can get the ones missing from 2015 and 2010, and I think there's one missing from 2014, I will do my best to get those ones done before the end of the weekend. I figure the other ones they have done, I think, on the Matt Oxford live stream thingy. The James Munro ones. He's really good, by the way. I love his explanations. I always think they're exceptionally clear. I don't know how you find them, but I just like the way he does things. And every time I think, I wish I could explain it as well as that. So yeah, do take a look at those if you haven't had a look at them yet. They are well worth a look. The other thing I wanted to say was, however well the exam goes on Wednesday, I hope it goes brilliantly, obviously. But seriously, if it doesn't go well, remember, you'll remind yourself that you're doing one of the hardest exams that you can do when you're 18 in mathematics, and I mean worldwide. It's, obviously this exam is sat obviously by lots and lots of international students anyway who are hoping to go to Oxford. It's one of the best unis in the world, and obviously if you're doing if you're doing it for Warwick or Imperial or something like that, it's a fantastic achievement to get any of the questions right on this paper. It really is a tough paper, so don't beat yourself up too much if you don't do as well as you hoped. You're still a fantastic mathematician, I'm sure of that. Okay, anyway, without further ado, let's get on with it. So I've got a circle passing through the points minus 1, 0, 1, 0. Okay, now straight away, any coordinate geometry question, and there will be one, they love testing coordinate geometry. Start drawing a picture. It's impossible without a diagram. No one knows what they're doing in coordinate geometry without a diagram. You need it. The circle A is center MH and radius r. So, I mean, it doesn't matter if you put it above here or down here because you don't know. Oh, sorry, why am I putting it there necessarily? I'm getting a little bit ahead of myself. Let me just rub that out though. I'll just put a line back in. I knew this would happen. I drew it well firstly, and now it's all going. Fortunately, I do have a backup plan. I've got GeoGebra out again, so I can draw some lovely pictures of this question on there. Okay, but we know it goes through minus 1, 0 and 1, 0, and you've got to figure out its center and its radius, yeah? And it says determine M and then write R in terms of H. So it's as if M must be known. Now, just think about it. As soon as I started to draw it, I put like, MH say there. I can't remember exactly where I drew it, but then I thought, hang on, this isn't really doable, is it? Because like when you get a circle, if you draw any chord of a circle, its perpendicular bisector is supposed to pass through the center. That is a circle theorem, which I think it's much easier than the. I looked on the mark scheme just a second ago, and I was like, oh, I didn't use a circle theorem to deduce that m is zero. Like m is zero by circle theorems. And if you want to be more specific than that, to make sure you get all the marks, you can just say, perpendicular bisector of a chord passes through the center. So perpendicular bisector of chord, yeah, and I mean the chord which lies on the x-axis, must pass through center. That's the reason why m is 0. That's the easiest way of getting m as 0 there. That is a fact for any 2 points on a circle. If you ever draw a circle and take any 2 random points, the perpendicular bisector must pass through the center. In fact, the way I've normally described this is I've said if you wanted to judge a freehand circle drawing contest, look at that, it's a perfect circle there. One way of doing it would be to take, a random pair of points, find the perpendicular bisector, find another random pair of points, find the perpendicular bisector, and find another random pair of points, find the perpendicular bisector. And the better the circle is, the more those lines should be passing through the same common point. So yeah, anyway, that's how I deduced that m was 0. So straight away I knew m was 0. Great, that's kind of nice. So I got rid of mh then. However you did it though, obviously if you did it in a different way, that's absolutely fine. And now to find h, well, if I just find the distance from that to one of the points that lies on the circle, the distance from there to there, that should find me the radius. Well, clearly that is h and that is 1. And so we've got r squared is 1 plus h squared by Pythagoras. Now they want r in terms of h, so r is the square root of 1 plus h squared. And that's that little one done. So that's a nice little starter. I didn't think that was too bad, and I didn't mind part two either, although it's pretty weird because part two, given a third point, x0, y0, so we've got this point, and one more point, and they've said y doesn't equal 0. That's interesting, and we'll explain why in a second. Show that there is a unique circle passing through the 3 points, minus 1, 0, 1, 0, and that. Now, what they're saying is you can't draw two different circles with 3 points on it. Well, GeoGebra seems to be very much aware of this fact, because if I can just flick to my GeoGebra, yeah, 1 second, I'll just take it over here. Right. Okay, so this is GeoGebra, and it's actually got a function where you draw a circle through 3 points. So let's see what happens when I select minus 1, 0 and 1, 0. Oh, straight away it starts trying to draw a circle. And wherever I've moved my cursor, it's saying, oh, is that where you're going to put your third point? Is that where you're going to put your third point? If I put it so that y is 0, I don't get a circle. I get a straight line because the 3 points are collinear. And you can't draw a circle through 3 points which lie in a straight line. But anywhere else is fair game. Slightly off of collinear, that just draws a massive circle. Down here, basically if I get quite near to yeah, there's certain values I can't pick as well, but I mustn't go on the line. I mustn't have y equal to 0 basically, but otherwise, yeah, I can put it anywhere, and look, it's unique. Now that's like just a graphical example of what we're trying to prove, yeah, and I'll prove it with algebra, but I just wanted to point out, it shows it nicely on GeoGebra. You want to get, whether you use Desmos, GeoGebra, something like that, get a decent graph drawing package because they're really, really useful. Okay, so that's what I just really wanted to say here. So how can we prove this algebraically? Well, we know from part one that the circle with points minus 1, 0 and 1, 0 has equation, try and explain what you're doing. I don't think I've been very good at that on my videos. I actually write a fair bit more down on, my answers to these questions. But you've got x minus 0 squared, haven't you? Because it lies on the y-axis. So you've just got x squared plus y minus h squared equals r squared, yeah? But r squared is just 1 plus h squared. So let's get rid of r squared and write 1 plus h squared. Yeah, and that's just from the general equation of a circle, which you should be aware of. Yeah, so that's what we know from part one. Yeah, now a third point must satisfy this equation. A specific value of x and y satisfies this equation. Should we give it a name? Let's call it star. It's nice to do that in your explanations. It lets the examiner know exactly what you're doing. Okay, so let's plug it in. If it satisfies it, plus, and I'm going to multiply it out as well. I hope you don't mind me doing that in one go. Y squared minus 2y0 h plus h squared equals 1 plus h squared. Now, the way you're going to get more than one answer is really with the h squares, but they cancel. And so when you rearrange this to make this h equals, because this is what I'm interested in, like if it's got two different answers, then there should be two different values of h. Yeah, if it's only got one unique answer, then there's one specific h for each x0 and y0 you pick, and that's surely the case here, because if I rearrange this, I get x0 squared plus y0 squared minus 1 over 2y0 equals h. And I'm going to be using this equation later on in this question, so it's really kind of useful. Let's in fact highlight it right now, because it's really useful, that. Oh, and that one's quite useful as well, so I'll highlight that. Okay, so I do need a little sentence now explaining clearly then each point x0, y0 corresponds to just one value of h. I should put each distinct point there. Each distinct point x0, y0 corresponds to just one unique value of h. And you can see that from this equation here. And that, and that proves the result. It's not like we're getting, if we wanted to get two different circles, which is what the question's implying, then I'd need two values of h popping out there. Because given a third point, show that it is a unique circle. Now, why is this a unique circle? Well, because once you've got h, that's what I wanted. I was thinking, what I wanted to say one more thing. I might put one more thing after this. So to just one unique value of h, and this determines the radius, the center, and the radius of the circle, because the center is h 0h, if you remember. That's what we proved in part 1, and the radius is dependent upon h. Yeah, there we go, done. Okay, so that was part 2. Okay, what about part 3? Part 3 is where it really gets fun. Now, I've actually drawn a picture of this because I thought, what are the chances I'm going to be able to do this with my graphics tablet? Obviously, when I was working on the question earlier, when I was just doing it like on a bit of paper, sitting on my sofa, I drew my own pictures. Yeah, I didn't have, you're not going to have the luxury of a perfect diagram like this. But so it really does help to draw nice diagrams. Now, I'm not brilliant at art. I'm really not. I got a C in my technology and art GCSE many, many years ago, and I'm proud of that C actually. But what I'm saying is, you don't have to be, Michelangelo to draw these diagrams. You can do it. You really can. Just try and improve on it because it does help your maths. It really does. Okay, so this is what we've got. We've got, I think this is this is circle B, and this is circle C, and that's from this description over here. Yeah, we're going to consider three circles A, B, and C, and they all pass through -1, 0, and 1, 0. Notice my ones all pass through -1 and 1. But then you're told A passes through 1, 2. So how am I going to start drawing A? Well, I know it passes through 1, 2, and mine 1 does up here. But I also know, as soon as I know that third point, this tells me H, and H tells me R. So I know everything about the circle. I suddenly know its center, which is determined by H, and its radius, which is determined by H. So all I have to do is plug in 1, 2 into this, and I get, 1 squared plus 2 squared, that's 5 minus 1, 4 over 2 times 2 over 4, over 4. In other words, h equals 1 for that one. In other words, this one should have a center of 1, and indeed it does. Now, to find the radius, I just need to plug 1 into here, and I get r is √2. That makes a lot of sense because the distance from there to there will be √2. So that's how I did circle A. Likewise, circle B and C. B is just going to be, right, plug in 0, 1. Well, this one's dead easy. You can even do this without looking because you've got -1s, it goes through that one, and this one. Well, that's clearly a circle which is just center 0, 0, radius 1. But certainly if you plug 0, 1 in here, you get 0 plus 1 -1 over, whatever, because that equals 0, and then plug in 0 into there, you get a radius of 1. In other words, it's center 0, 0, radius 1. Same for C, 0 -4, just plug it in. You actually get like 15 over -15 over 8 here, so you don't get a nice value for H. Your R ends up being, I think, 17 over 8 once you've done the Pythagoras. But don't worry too much about that. It almost feels like a bit of a distractor in this question, actually. But yeah, the center of it is, in fact, -15 over 8 and 17 over 8. For the radius. I did write that down on my diagram as well. So it's, because it's not completely, it's like -15 over 8, 0 obviously, -15 over 8. And if you care, that is 17 over 8. I did work that out. Subsequently realized it was a bit of a waste of time, but there we go. I'll show you why. It's almost there just as a distractor, that one. Now, I suppose it comes up in part 4. But yeah, what we got to do? Let's look at this really carefully, this definition of lopsidedness. Its lopsidedness is a fraction of the full area of the circle. Well, that's easy. I'll just work out the area taken by its largest region. Yeah, so we've got to find the fraction of the full area that is taken by largest region. Now, what's the largest region? When we're doing the lopsidedness of A, what is the largest region looking at our diagram? Well, it's quite clearly the big sort of crescent moon on its side there. That is the largest region, so I need to find that area. And once I've found that area, I need to find that fraction of that area is of the whole circle. Now, that's okay, because as you can you see very quickly, that's nothing to do with C. Yeah, that's everything to do with B and nothing to do with C, because that line is playing no role in this lopsidedness calculation. I need to find this area. Let's cross it actually. I should have done it spotty or something like that, or even in a different color. I need to find that area, sure, and I need to find the area of the segi. I'm going to take all of these lines off now. That's how I'm going to try and find the crescent moon area. So to give you an idea, well, firstly, let's just find the area of A. Yeah, the whole circle. Well, that's just pi r squared. And if you remember, I said r was root 2 for this one, because it's distance from there to there, so that r is root 2. And so that's just going to be root 2 squared, 2 pi. Okay, here's the tougher bit. Now, this isn't so bad, though. If you do lots of coordinate geometry, you will get used to these kind of questions. They're not easy, but I promise you they're doable. If I can do them, you can definitely do them, my friend. Okay, here we go. I just figured if I draw a line down there, I think that I can work out that question, because if I want to work out that segment, that's what it is, it's a segment, then I just have to do sector area minus the area of the triangle. That's what I'm going to do, sector area minus the area of the triangle. And then I've got the segi area. And then if I take that away and also take away the area of half a circle of radius 1, which I can definitely work out, from 2 pi, I'll be left with the crescent moon area. So I hope that makes sense. That's my overall strategy. So I tell you what, let's work out the area of, yeah, let's do the segi bit first, because the segi bit's the hard bit. Okay, so segi area, let's call it segi area. Okay, all I'm going to do for this is I'm just going to know, well, hang on a second. If I'm working out the area of the segi, I'll work out the area of the whole sector, which is actually just a quarter of that big circle, isn't it, with a radius root 2. It's a quarter of A, because that must be 90 degrees. Why must it be 90 degrees? Because that's 1, and therefore that's an isosceles right-angled with that's 45. Same on the other side, that will be 45, so that will be 90. And so I can easily work out the segi area by doing the area of A, which I already know is 2 pi, and divide it by 4. Minus the area of this triangle where I've got the base and the height. So minus a half times by 2, distance from -1 to 1, times by 1. Yeah. So the segi area is pi over 2 minus 1. Yeah. Let's just write that underneath a bit clearer. Pi over 2 minus 1. That's the segi area. That's a bit down here. Yeah. Now, that's not that bad. And that's the hardest bit of this part. The spotty area, if I can just spot this area, that's just half the area of a circle of radius 1, yeah? So if I can just put down casually here, spotty area is going to be pi times 1 squared divided by 2. Well, that's pi over 2, yeah? And so, finally, the area of largest region is just going to be the total area of the circle A minus the spotty area, pi over 2, plus the segi area, which is pi over 2 minus 1. And so what have I got here? I've got 2 pi minus a pi, which is pi, and then a plus 1. And now I can work out the lopsidedness, because I just wanted it as a fraction. The lopsidedness must be the whole area of the circle is what we're going to divide by, and then the area of the region is what we'll have on top. Pi over 1 divided by 2 pi. Done. So yeah, not too bad, that one. I really didn't think that was too bad. Now, what about the next part? Didn't mind part 4 either, unusually. Quite often I really get intimidated by the last part of a math question. More often than not, I'd say, the last part is like, oh, this is a hard bit. But remember as well, it's normally where the marks are, so the battle is kind of won and lost on the last couple of parts of these long questions. I'd be careful with them. Now, okay, I'll try and draw this as well, because I did draw it by hand, like I say, when I originally do it. And trust me, I do have a steadier hand than this. I know it looks like I've been drinking, but I'm so bad on the graphics tablet. I'm getting better, but I'm so bad. Okay, so what have we got here? Now let A pass through 1, 2p. That's just like 1, 2 before. So I'm going to draw it in a similar way. It was like a big circle. I'm going to imagine P is 1, basically. And that's like the circle A. B still passes through 0, 1. So I'm going to draw that exactly as before. Remember, these are supposed to be passing through, as mine aren't, the same point. They're supposed to be passing through the same point. Yeah? And then what about C? Well, that's minus 1, minus 2p. Now, straight away I notice, well, if it's going through 1, 2p, on this side, it will also be going through minus 1 2p. Yeah, and that's just because you should have a nice, arrangement here, like where. Oh, and by the way, it's worth noting as well the center of this, because this is 2p, yeah, and we have this like symmetry thing going on, that these ones are lined up with these ones. This is just going to have a center of p. Now you can work that out anyway by plugging this in here. You'll get 1 plus 4p squared minus 1, so that's 4p squared over 2 times 2p, which is 4p. So you get 4p squared over 4p, which is p. In other words, the height is p, but you can kind of see it just from the diagram. Now, what that tells you is that, like, when you've got minus 1, minus 2p, you're going to get a lovely bit of symmetry there. And it's going to be the same down on the bottom. It's going to be an identical circle, but upside down on the other side of the axis. That is terrible, isn't it? Like, you can see why they didn't want to award me anything like a B grade in GCSE art. Now, yeah, by the way, that 2p it should be on the y-axis really, because it's the y coordinate, and 1 is on the x-axis. That's why I've got it lined up with that. I'm going to show you what it looks like nicely in a second, I promise you, but I just wanted to show you I can, because this is what you're up against. Yeah, I want to explain it first with my dodgy diagram, and then I'm going to switch to a decent diagram so we can see what's going on. But yeah, I want to explain what they're asking here, right? So they're saying, show that the value of p minimizing the lopsidedness of circle B this time. So it's B we care about this time, which is the middle circle, not A, not C. We want to minimize the lopsidedness of B. Now remember, lopsidedness is basically largest region divided by total area. Well, if you want to minimize the largest region, and B is split into 3 regions, then what you want surely is each of these regions to be equal. Yeah, and I'm talking about this region, and this region. Yeah, do you see what I mean? Those 3 regions should be exactly the same area. They really should. Because otherwise, if you make one bigger, then suddenly that's the biggest region, and suddenly you're not minimizing the lopsidedness, you're making it bigger. Let's say you think you can make this one smaller. Well, that just makes another region larger. So that's the reason why we want each of these regions to be equal. Yeah, once you've got that, it really isn't so bad. So overall, my strategy, once I drew a diagram slightly better, but not that much better than this, once I realized, okay, so like this region needs to be the same as that region, needs to be the same as that region, really, I was off, and it didn't take me very long to get to the answer at all. So let me just quickly show you like a diagram like that. Let's actually quickly do it on GeoGebra. Okay, so what did we want? We wanted one going like this. Let's try and get it as accurate as possible. Okay, and then we had one. I'll take the value of p to be 1 here just for the sake of this diagram. So we got that one, and 1 2. Oh, 1 2. And then same again, but down below. We'll get a nice little drawing that we can work with. 1 minus 2. There we go. Cool. And let me just get rid of some of these just to make things easier. Sorry that this video is probably going to be a little longer than you've got to do the question, but I do like to explain things, and I do like to faff around on my little GeoGebra thing. It does help, it really does, I promise you. Okay, right, almost ready. Right, okay, so, and I tell you what, let's just quickly take a screenshot of that. And yeah, then we can use it on here. Go away. Okay, so lovely. Now this is going to make it a little bit easier to explain what I was doing. I hope that it will be a bit clearer. Okay, so all I'm trying to do is I'm trying to make sure that the middle circle, like each region is divided into an area of pi over 3. Yeah, so let's actually tell the examiner that's what we're doing. Circle B needs to be divided into 3 regions of equal area to minimize lopsidedness. I'm just telling them what I'm doing there. Like I say, I do actually write down a fair bit. I'm not perfect, but I do write down a fair bit because I'm aware that they like people to explain what they're doing. Okay. Now, if I want to, right, firstly, circle B has area pi. And that's because it's just pi times 1 squared. And so that's pi. So in other words, we want to make sure Can we call them lips? It kind of looks a little bit like lips in the middle. We want to make sure that that area is pi over 3. Okay, so half of that area can be pi over 6. Now you might be thinking, well, why has he gone to pi over 6? Well, look at that, pi over 6. You know, it kind of gives you little hints in the answer, doesn't it? So we just need to show that this area is pi over 6. That's all we need to do. Right, well, that's not going to be a problem at all. So, you know, let's just quickly explain that like a diagram. If you label your diagram, that will really help, yeah? So if I can just put this here, and it's actually a segment, isn't it? And it's actually a segment, though, of circle. Let's not call it A because we've got circle A already. So we need to prove, in order to do this, we need to prove that the segment area is pi over 6. And let's just say the segment area labeled, I don't know, K or S maybe. S is always dangerous for me because it looks like my 5s. So that's what I'm trying to do. Well, let's work it out. We already know that this one, now this isn't actually going to be 1, it's going to be P in your example, yeah? So that's the first thing I'd say. Don't think that that is 1, that's P. It's an area of P. Okay, so what I'm going to do is I'm going to actually find the area of the segment now. Obviously, the segment area is going to be equal to basically sector area minus triangle. Oh, let's not be lazy, that's actually right triangle. And that's going to be equal to, okay, once again, well, no, actually, we can't use the fact that this is going to be 45 degrees. I'm going to use a half times by r squared. Now, remember, this circle actually has a radius of, let's write these important facts down because we're not dealing with one with a radius of 1. We've got 2p. And so do you remember I said h was p, and therefore this is going to be root 1 plus p squared. So I'm going to write down r equals root 1 plus p squared. And so the sector area of it is going to be a half r squared, which is 1 plus p squared, times by theta. Now, what's theta here? Well, I tell you what, I'm going to call this theta, yeah, and I'm actually thinking about it. I'm going to work out just this area first, and then I'm going to double it. So if I can do it like that, if I can do it like that, yeah, 2 times area of sector minus triangle. Yeah, and that way I can just work with this theta. Now you might think, why is he doing that? Well, it's because tan theta is going to therefore be equal to opposite, which is 1 over adjacent, which is p. Remember, that's not a 1, that's p. So 1 over p. Now, why is that a winner? Because look at this, it's arctan of 1 over p. Like, that's why you want to do that. So we'll just do 2 times that half times 1 plus p squared times by theta. Now theta's arctan of 1 over p. Yeah. And then I'm going to take away the area of this triangle here. Let me make it a bit clearer. That triangle. Yeah. And then at the end, because I've worked out that, I'm going to double it, and therefore that should equal pi over 6. And that's actually write that down now. So pi over 6 equals pi over 6 equals. Okay, the area of the triangle is just 1 times p times a half. But I'm doubling it, and basically the result falls out in the next line because you just get 1 plus p squared arctan 1 over p minus p. Yeah, done as required. You might want to write a bit more justifying what you've done there, but it's not that bad a question. It really isn't. I thought it was quite a fun coordinate geometry question. I'll try and get the rest finished soon for you. Best of luck in the mat.